In this video, we are going to look at non-regular languages. In other words, we would like to find out the how powerful how powerful regular languages are. Okay. So the question we would like to answer is, what languages are not regular? So first of all, we know that the memory capacity of a DFA is very limited, as we saw earlier, that DFA is equivalent to NFA, meaning that the languages accepted by DFA and the languages accepted by NFAs, they are just regular, so they are identical. Okay, so we can convert an NFA to a DFA, so that the converted DFA accepted the same language. Okay, then we also know that we can use states to memorize certain patterns, and the patterns states can memorize are static. Okay, so it cannot even be used to remember simple dynamic patterns, such as 0 to the n followed by 1 to the n for unbounded n. So for any integer n, because 0 to the n followed by 1 to the n involves counting. And that counting is dynamic because for any given string, you have to know the length. Okay, so that means it involves counting. And using states alone cannot do counting. Okay, cannot do counting at all. All right, so the theorem then says that this set of languages, the set of all strings, in the form of 0 to the n followed by the same number of copies of 1, okay, that means 1 to the n, is not regular. Then the question is, how do we prove it? So the idea to prove non-regular languages is to find properties that every regular language must have, and use such a property as a test for regularity. Namely, if we can prove that a language does not have this property, then it cannot be regular, right? It fails the test, so it cannot be regular. So the pumping lemma is such a property, okay? So now let's look at what this pumping lemma for regular languages says. So suppose L is a regular language. We want to derive properties that L must have. So here is a property. So if L is a regular language, then there is a positive integer P, such that for any string in L, okay, for any element in L, with length of s greater than or equal to p. So that means it's for any long enough element of L, this s can be written as xyz. Okay, so what that means here is that if x is long enough, say this is my input x, and let's say this is assuming this is in L. So this is, if x is long enough, so this is long enough, then, so long enough here just means, okay, we use s, not x. Okay, so this S is long enough. The length of it is greater than or equal to P. This is S, not 5, right? So let me rewrite it. All right. S. All right. Then S can be divided into 3 portions. Okay, so this is X, Y, Z. So that's what this says. Okay, as long as it's long enough, then it can be divided into 3 portions. And then we're going to see what properties these substrings would have or must have. First, this Y is not empty. So that's length is greater than 0 means that Y is not an empty string. X could be empty, Z could be empty, but it doesn't matter. As long as Y is not empty, that's what we need. And then it also says this prefix, okay, of S, that's XY, it's not too long. So in other words, it cannot be, the length of it cannot be more than P. So it's less than or equal to P. And Y here is not empty. Okay, so this X, Y, Z. So these are properties X, Y, Z must have. And then you can pump Y. So that means that for any, so that means this, now this is very important. That's where the name pumping comes from. So we can pump Y up or pump Y down. So that means I could be 0. When Y is 0, we remove Y. The new result, the new string, I'm sorry, the resulting string, one is XZ when I is equal to 0. The other one will be any copies of Y, Z. Okay, so these, oops, it's very hard. I need to get a better pen here. Okay, so this is a pumping. So this is a pumping down. This is a pumping up. So the resulting string will also be in L. So this is in L. This is also in L. So that is the properties these substrings X, Y, Z must have as long as your input string S is long enough. And how do you quantify long enough? So we use an integer P. So there's a P in existence, okay? We don't, depending on what L is, then so that P depends on L, okay? So this P depends on L. Can I write it down here? Okay, P depends on Line up. Depends on L. Okay. All right. So that's what this property says. So now let's look at how we prove this pumping lemma. Okay. The proof of this pumping lemma is actually pretty straightforward. So first, because we know that L is regular, that means there is a DFA, let's call it M, such that DFA accepts L. So now we simply let P to be the number of states in M. Then for any input S in L, for any string S in L, with length of S greater than or equal to P. Okay, so this is greater than, this is a typo. This is greater than or equal to P. It had to be long enough. Then we let S be the prefix of S of length Q. Then, okay, any accepting pass for S prime must have a cycle because so what you'll have here is from the initial state to a accept state. Oops. Do it again. So this is initial state. This is accept state. And this is your S. Okay, and then there's certain states you go in between, right? So of course, some of these states, when S is long enough, has to be repeated. So what you are looking at, since we know the length of S is greater than or equal to the number of states in this DFA, so that means I just look at the prefix here. So if this prefix, let's call it S prime, its length is, let's say it's Q. So this is P. It's the length of it, it's Q. The length of the size of Q. Then then the number of states in this portion up to here, okay? So then the number of states on this portion, on this path, the number of states on this path is P plus 1. Right? Or the size of Q plus 1. Let me just use that. So that, because the length, the number of states is always one more than the number, the number of, so each edge represents a symbol. So the number of states is always one more than number of edges on that path. So you have, so the number of states on this portion is the size of Q plus 1. So since you only have this many states, that means at least 2 of these states will have to be the same. Okay, so let's say this state and that state are the same. They are the same. Okay, so that means I call this strings between these 2 states, y, and this will be x, and after this solid one will be, so this part will be z. Okay, so then you can see here, if I remove this segment, if I remove this part, that means when x go to this solid state, you can immediately go, you can go to the next one, right? So because this is the same state, so there is a choice, you go to the next one. And then of course, you also go here. Okay, so you accepted it. You accepted it, so you can remove y, you still have acceptance part. You remove y, because this y is no longer there. Then you use, so say your input doesn't have this y portion in it. Then once you get in here, because you don't have y's, and then you just read it here, then you can also accept. So this is accepting path. Similarly, you can repeat this y many times. Okay, you can still get accepting. So repeating many times because, so once you are here, because this can repeat, so from here you can repeat y, so from here you can, from here you read y, you end up here, so from here you can also read y, you'll still end up the same state, right? So you can repeat it many, many times. So hence, you have this pumping lemma. So that's the idea of this proof. So proof is straightforward. So now let's look at this writing. So because we have a DFA that accepting L, we let P be the number of elements in Q. That means the number of states contained in M. Then for any S in L, if S is greater than or equal, so when the size of S is greater than or equal to P, let S prime be the prefix of S of length exactly P, okay, which is the size of Q. Then the accepting path for S prime, this portion, must have a cycle. That means it must have, so this is a cycle because these 2 states are the same. So it is a cycle. Okay, so in other words, you can think of it as that. So this is initial, this is solid state. You'll just combine into one, and this is your y. That's a cycle. Okay, so go into some other nodes, and then go to the accepting state. So this is your z. This is your x. This is your initial state. So that is a cycle. Okay. So then let this portion be x. That means from this initial state to Q, the first Q, right? And y, the substring on the cycle. Then xy is a prefix of S prime, and y is not empty because of these 2 states. There's something in between you have to read, and because this is a DFA, so you got to read something. To end up at this state. And also we know that from x, so x and y here, the because these two states are the same. So for this part, okay, the size of it, the length x and y cannot be more than p. Okay, cannot be more than the state of Q, the number of states in Q, number of states. Okay, so and also y is not empty. All right, so that then you can pump it up and you can pump it down. So that is the property that every regular language must have. Okay, so now this is a pumping level visual from your textbook. Okay, so this is the initial state. Okay, you go to Q0, and this part is your Y, and then this is the Z, right? So, and we already saw that. So once we have this property, then we can use it to prove non-regular languages, to prove non-regularity for a given language, if that language is not regular. Okay, so here is a language that we mentioned earlier, which is a set of strings. It begins with n zeros followed by n ones. This involves counting because you have to count number of zeros before number ones, and the number of zeros must be the same of number of ones. Must be of the same to the number of ones. Okay. So we use pumping lemma. That means now we want to show that this L does not have this pumping property. In order to do that, we just use assumption. So we assume that L is irregular. Then we can apply the pumping lemma. So that means that then there exists a positive integer p as stated in the pumping lemma. Okay, so that means for any input, for any string s in L, when the length of s is greater than or equal to p, then s can be divided into x, y, z, and such that xy is the length of xy less than or equal to p, and y is not empty, and then you can pump y up and pump y down to still have a string in L. So that means we can select, in order to prove contradiction, we can just pick a particular s. So in this particular case, it is straightforward to pick s to be 0 to the p followed by 1 to the p. So the length of s now is equal to 2p, which is greater than or equal to p. So it satisfies the condition of the pumping lemma. Then by the pumping lemma, there must be substrings x, y, z, such that s is equal to x, y, z. The length of xy is bounded above by p. Y is not empty, and for all I greater than or equal to 0, x, y to the i's power z is in L. So that means you can pump it down and pump it up. They are still in L. So because the size of xy is less than or equal to p, so xy must be a prefix of 0 to the p, because the length of 0 to the p is already p. So it has to be, xy has to be a prefix of 0 to the p. Hence, you remove some zeros off by pumping it down. So that's what xy to the z's power, xy to 0 followed by z, then it is equal to z0 to the p minus length of y followed by 1p, because y is greater than 0. So now you have a strictly smaller number of zeros before number of ones. This string is not in L. Okay, but by pumping lemma, this string, okay, when I is equal to 0 is in L. So By the pumping lemma is in L, but it implies this string is not in L. So that contradicts. That's a contradiction, contradicts to this pumping lemma. So that means we know the pumping lemma is correct, so that the contradiction only can only come from your assumption that L is regular. So hence, L is not regular. So that is a proof. So from this proof, you can see that first you need to understand the pumping lemma, what properties that pumping lemma indicates for the regular language. And then it's important to choose a string that depends on P from the pumping lemma. Okay, so the easiest choice to choose it is to just use that P for your for the string you choose, and that's in L. Then depending on your question, you can either pump it down or pump it up. So next let's look at another example. So we let A be a language is consisting of binary strings with equal number of zeros and number of ones. Then A is not regular. Okay, so this is the same pool we can use. We can use the same pool from the previous slide, because we can just choose a particular string S in this particular form, 0 to the P followed by 1 to the P, so it has the same number of zeros and same number of ones, which is in A, but you can pump this part down, then you get a string that has strictly less number of zeros than the number of ones, and hence the resulting string is not in L. That contradicts to the pumping lemma. And that contradiction can only come from the assumption that A is regular. Hence, you prove that A is not regular. So this is a pumping down. So now let's look at another example that we will need to pump it up. Okay. So in this, so we let B be 0 to the I followed by 1 to the J such that I is greater than 0 but strictly less than J. It's still counting, okay? But in this particular case, we can also prove that B is not regular. So now remember that your prefix X, Y would be in this portion. So we would need to pump it up in this time. So again, we assume that B is regular. Then by the pumping lemma, there is a P, right? So let P be the positive integer stated in the pumping lemma for B. As we said that. As we said earlier, that P depends on your language, okay? So when B is given, and if B is irregular, then we can find that P. P is, again, is from our proof, we know it is the number of states in a DFA that accepts B. Okay, so now we just pick a string to be in B, which is 0 to the P followed by 1 to the P plus 1. Now P is positive, so it's greater than 0. And P is strictly less than P plus 1. So this string is in L. So then we repeat the pumping lemma. So that means there are X, Y, Z such that S is equal to X, concatenate Y, concatenate Z, where the length of X, Y is less than or equal to P, Y is not empty, and you can pump it up. So we can just pump it X, Y squared Z to B. Okay, once you pump it up, the new string is this. Okay, you have one more copy of Y. So if we let the length of Y be K, which is greater than or equal to 1, right? Because it's greater than 0, that means it's at least 1. So we get x, y, y, z is actually b, 0 to the p plus k followed by p plus 1 because k is greater than or equal to 1. The number of zeros here is at least the same as number ones, which then is not in B. However, your pumping lemma says it is in B. Hence, this contradiction says that your assumption that B is regular is wrong. Hence, B is not regular. Okay. So as you can see here, proving a language is not regular. When you use a pumping lemma, it's important to choose an appropriate S depending on P so that you can work on S either by pumping a portion of Y down, meaning removing Y, or pumping it up, add more copies of Y to make a contradiction, to find a contradiction. All right, so that is the end of this video.